Hi there. Welcome back to our lesson series where we evaluate a design problem of a process to produce methanol from carbon dioxide and hydrogen. Here in Lesson 3, we are continuing with the second part of the question where we are required to use the knowledge gained in Part 1 to propose and solve a more reasonably defined design problem with better specifications. And we are further required to use CAMCAD to simulate the newly defined design problem. Recapping where we are at this point, we have already done quite a bit of work on redefining the problem in previous lessons. The first outstanding activity right now is that we need to provide the correct feed flows to produce 53 cubic meters per hour of water-ethanol mixture from the reactor. We also need to incorporate friction loss calculations in the pipeline of the stream after the reactor as specified in the problem statement. Remember that this piping data was meant for calculations that were meant for sizing the pump. We have declared that we do not need a pump as the stream from the reactor has very high pressure, and we have proposed to use this pressure energy to overcome piping momentum losses. The flowsheet of the proposed problem now looks like this. We still need to add the pipeline sections to do pressure drop calculations. In order to do the correct feed flow rates in order to produce the required flow rate, let us check what is the current liquid flow rate of the stream while using the currently specified feed flow rate of hydrogen and carbon dioxide. Let us open CAMCAD and check what the equivalent liquid flow rate of the current simulation is. Remember, at the current conditions of the simulation, the stream from the reactor to the distillation column is a mixed two-phase of gas and liquid. However, CAMCAD gives you the liquid volumetric flow rate of that stream, as it would be if the conditions allowed it to be liquid. We can see that the standard liquid volumetric flow rate of this stream is 58.0377 cubic meters per hour. In order to adjust the equivalent liquid flow rate from the reactor to be the specified value of 53 cubic meters per hour, we can adjust the currently stipulated feed molar flow rates of hydrogen and carbon dioxide by multiplying them by a factor of 53 divided by 58.0377. We can now enter these adjusted value into CAMCAD. Once we have adjusted the values and run the simulation, let us check if these adjusted values produce the required volumetric flow rate of the product. That's fantastic. The standard liquid volumetric flow rate of the stream leaving the reactor is 53 cubic meters per hour as required. Now, the next and last part of this project is to add the pipe sections specified in the problem statement in the simulation to calculate the pressure drop due to friction losses in the pipeline and fittings. The information that is specified here does not state which diameter is given here. We will assume that this is a Schedule 40 pipe with 200 mm diameter. Let us first enter the first pipe section into the simulation. We are going to insert the pipe section on the stream here. We will use Insert Unit Op option to insert the pipe section. Right-click on the stream, click Insert Unit Op, and then drag and drop the unit operation you want to insert. In this case, it is a pipe section. Double-click on the unit op to provide specifications. We know that the stream is not a single flow system, as we have two phases. We will use the Beggs and Brull two-phase flow method to do the calculation, as it is the most accurate for most cases. We said the pipe schedule is 40. The nominal diameter is 200 mm. There is no elevation specified. The roughness factor is 0.055 mm, which translates to 0.000055 meters, as the units used here is meters. Now let us specify the valve fitting. It is L/D specified, so we will use that option. The value of L/D is 18, and there is only one valve. Let us now change exit pressure from the valve back to 5 bar. Let us now simulate the two unit operations that we have changed and check the pipe section calculations. The first value we will look at is the liquid velocity in the pipe. The velocity is 70.4 meters per second. This is way too high. Remember from pump specification lessons that, as a rule of thumb, the liquid velocity should be between 1 and 4 meters per second. We will have to change the nominal diameter of the pipe to get a more reasonable velocity. Clearly 200 mm is too small. Let us choose the highest nominal diameter of 900 mm, and run the simulation to see what would be the liquid velocity. The velocity is now at a reasonable value of 3.77 meters per second. We will take the nominal diameter of all the other pipe sections to be 900 mm. Now let us proceed and insert those pipe sections. This will conclude the end of our step-by-step guidance through this assignment. You can now complete your assignment and write about 20 to 30 page report of what you have discovered, supported by reasons from theory, calculations, simulations, and references. Good luck and goodbye for now.
Thank you very much for studying with Tutor.me Open College. Please click subscribe so that you are kept updated with new learning material as it is being updated. If you like this video, also, please click like so that the video is recommended to other learners such as yourself.